the next session. Now in this session, we discuss the definition of analytic function, followed by Cauchy-Riemann equations, bilinear transformations, and then if possible, we discuss classroom workbook also. Now, let us recall the definition of analytic function. Suppose we have a complex valued function f of z and z0 is a complex number. We say that f of z is analytic at this point if f of z is differentiable at all points in some neighborhood of z0. When you look at the neighborhood of z0, it will be in the form open interval z0 minus epsilon comma z0 plus epsilon. This is an open interval. Here epsilon is a number which is greater than 0. Suppose if this is z0. Now this is one neighborhood. This is another neighborhood. This is another neighborhood. This is another neighborhood. Like this, when you change frequently epsilon values, a particular number will have infinitely many neighborhoods. I don't require all these neighborhoods. If at least f of z has a derivative at all points in at least one neighborhood of z0, my job is over. Okay. So whenever f of z is differentiable at all points in some neighborhood of z0, then we say that f of z is analytic. So this is one neighborhood, second neighborhood, third neighborhood, like this. So change frequently epsilon values, you can produce infinitely many neighborhoods for a same point z0. I require single neighborhood. If at least in one neighborhood f of z has a derivative at all points, then we say that f of z is analytic at the point. Let us take examples. Suppose f of z equal to z square. We know that all polynomials are differentiable at all points. In particular, if you take z square, it is analytic at all points because it has no singular points at all. When a function has no singular points at all, it is analytic at all points. Okay. Even you can take constant function. So f of z equal to 3, constant function. You can take sine function, cos function, exponential. All these are analytic at all points. So let me write out all examples. First example refers to polynomial, constant function. Third example refers to exponential function. Fourth one, f of z equal to sine z. And fifth one is f of z equal to cos z. Therefore, all these functions are analytic at all points in the entire complex plane, and such functions we call them as entire functions. We call them as entire functions. That means in the entire complex plane, they are analytic. Therefore, in particular, they will be called as entire functions. First, write this definition. Very simple definition. A function f of z is said to be analytic at a point z0. A function f of z is said to be analytic at a point z0. A function f of z is said to be analytic at a point z0 if f of z is differentiable at all points in some neighborhood of z0. If f of z is differentiable at all points in some neighborhood of z0. Examples: all polynomials, comma constant functions, all polynomials, comma constant functions, comma e power z, comma sin z and cos z. All polynomials, comma constant functions, comma e power z, comma sin z and cos z, or analytic at all points, or analytic at all points in the entire complex plane, in the entire complex plane. Now, Let us see the relation between analytic function at a point z0 and differentiability of a function at a point z0. We have two important aspects. One is analyticity of a function at z0, differentiability of a function at z0. So my comment is, whenever a function is analytic at a point z0, implies it is automatically differentiable at z0. This is very obvious thing. Why it is obvious thing? Because when you go to the definition of analytic function, what it says, if f of z is analytic at all points in some neighborhood of z0. See, when you take any neighborhood of z0, the neighborhood itself contains the point z0. Got it? So therefore, whenever a function is analytic at a point z0, implies it is differentiable at the same point, not this point. Note, if f of z is analytic at a point z0, if f of z is analytic at a point z0, then f of z is differentiable at z0. Then f of z is differentiable at z0. Then f of z is differentiable at z0. Next concept, Cauchy-Riemann equations. Popularly they will be called as CR equations. Very, very important. CR equations. So one equation is introduced by a famous mathematician Cauchy. Second equation is introduced by the famous mathematician Riemann. Generally, we discuss integrals, integral a to b f of x dx in the real integration. Those integrals were introduced by the famous scientist Riemann. That's why they called Riemann integrals. Okay. Even we have seen Cauchy results. That means Cauchy's mean value theorem in the differential calculus of chapter 3. So these two fellows are famous mathematicians. They contributed a lot in the entire mathematics world. Okay. Now let us see how it is useful in case of complex variables. Suppose we have a complex valued function f of z. Since it is a complex valued function, it can be expressed in the form u of x comma y plus I into v of x comma y. This is a complex valued function, so this can be expressed in the form u of x comma y plus I into v of x comma y. Suppose if it is analytic at a point z0, assume that it is analytic at a point z0. Since it is analytic, it is differentiable at z0. Implies the first order partial derivatives of u comma v exists and they satisfy the equations ux equal to vy, uy equal to minus vx, ux equal to vy, uy equal to minus vx at z0. And these are called Cauchy-Riemann equations. What is ux? Here in this case, ux equal to dou u by dou x. Here u is a function in the two variables x and y. Ux is dou u by dou x. Uy is dou u by dou y. Vx refers to dou v by dou x. Vy is nothing but dou v by dou y. So therefore, whenever f of x equal to f of z is u plus iv is analytic at a point z0, implies it is differentiable. That is very clear. Since it is differentiable, we can discuss ordinary derivatives as well as partial derivatives. But here u contains two variables x and y. V is a function in two variables x and y. So normally we discuss partial derivatives. Therefore, you can discuss dou u by dou x, dou u by dou y, dou v by dou x and dou v by dou y. So all first order partial derivatives ux, uy, vx, vy exist and they satisfy the equations ux equal to vy, and uy equal to minus vx at the point z0. Here I can write this z0 as a complex number x0 plus iy0. This can be equivalent to the points x0 comma y0. Now let me explain what does it mean. Here calculate dou u by dou x, and this must be equal to dou v by dou y when x is replaced by x0 and y is replaced by y0. Similarly, dou u by dou y must be equal to minus of dou v by dou x when x is replaced by x0 and y is replaced by y0. So therefore, whenever f of z equal to u of x comma y plus I into v of x comma y is a complex valued function which is analytic at a point z0. What is my point z0? x0 plus iy0. Now that is equivalent to the 2D point x0 y0. Since it is analytic, automatically it is differentiable. Since it is differentiable, the first order partial derivatives, I am not sure about second order partial derivatives, but regarding first order partial derivatives, we can give 100% assurance. So dou u by dou x must be valid number. Dou u by dou y, dou v by dou x, dou u by dou y, all first order partial derivatives of u comma v exist at the point z0 and they satisfy the equations ux equal to vy, uy equal to minus vx at the point z0, and these two equations are called as Cauchy-Riemann equations. Okay, note these points. Let f of z equal to u of x comma y plus I into v of x comma y. Let f of z equal to u of x comma y plus I into v of x comma y be a complex valued function, which is analytic at a point z0. Let f of z equal to u of x comma y plus I into v of x comma y be a complex valued function which is analytic at a point z0 equal to x0 plus iy0. Analytic at a point z0 equal to x0 plus iy0. Then the first order partial derivatives of u comma v exist. Then the first order partial derivatives of u comma v exist and they satisfy the equations. Then the first order partial derivatives of u comma v exist and they satisfy the equations ux equal to vy comma uy equal to minus vx at z0. ux equal to vy and uy equal to minus vx at z0, and these are called Cauchy-Riemann equations. Where ux equal to dou u by dou x comma uy equal to dou u by dou y comma vx equal to dou v by dou x comma vy equal to dou v by dou y, right? So whenever f of z is analytic at one point, if the function has representation like this, these many things will happen. Okay, now let me tell you the importance of these things after a few minutes, but let us at this moment let us try to understand the converse of this statement. Now just now we have seen the point. If it is analytic at a point z0, then CR equations must be satisfied at a point z0. So in simple words, we can write like this. If f of z is analytic at a point z0, implies CR equations must be held at z0. Second point is, now if a function f of z satisfies CR equations at a point z0, it may or may not be analytic. Even I can discuss this also. If a function f of z is analytic at a point z0, implies it is differentiable at z0, implies CR equations must be held at the point z0. So at first, let us take this equation. So f of z is analytic at a point z0. A means analyticity. If f of z is analytic at z0, implies it is differentiable at z0, implies CR equations must be whole. So therefore, I am replacing this analyticity by differentiability. So f of z is differentiable at a point z0, implies CR equations must be whole. What is the converse of this theorem? If a function f of z satisfies CR equations at a point z0, it may be differentiable at z0, it may not be differentiable at z0. Therefore, the converse of previous result may or may not be true. Even counter example is not required, but the importance of these points I can tell you after few minutes. Okay, so be patient for few minutes. If f of z satisfies the CR equations at a point z0, it may or may not be differentiable. In some cases it may be differentiable, in some cases it is not differentiable. Point 3. Suppose if a function satisfies the CR equations at a point z0 and u of x comma y comma v of x comma y are continuous at z0 then f of z is differentiable at z0. So this is very powerful point to say a function is differentiable at z0. So a function satisfies CR equations at a point z0. My task is to decide whether a function has a derivative at a point z0 or not. One thing is by using definition, f dash of z is limit h tends to 0, f of z plus h minus f of z by h. If you unable to go for expansion of limit, then apply CR equations. So I have a function f of z. Assume that it satisfies both CR equations at z0. Then it may not assure that it is differentiable. But if f of z satisfies CR equations at a point z0, both the CR equations, and u of x comma y comma v of x comma y are continuous at z0. If they are continuous, ultimately their partial derivatives ux, uy, vx, vy are continuous at z0, then f of z is differentiable at z0. You can take either this or this, but I will follow this. I will get many advantages. So what is my statement 3? A function f of z satisfies all CR equations at a point z0 and ux, uy, vx, vy are continuous at z0. Implies f of z is differentiable at z0. Now point 4. If f of z does not satisfy any one of CR equations at z0, then the conclusion is f of z is not differentiable at z0. Then f of z is not differentiable at z0. This is very, very effective point. So in the future, if you want to say that f of z is not differentiable at z0, you need not go by limit expansion. Just try to expand that function in the form u of x comma y plus I into v of x comma y. So verify CR equations. If you prove that any one of these CR equations failed at the point z0, then ultimately the function is not differentiable. Okay. So I can apply this for many points. So note all this. First, already we have discussed this point. Now let us try to start from this point. Note, if f of z satisfies CR equations at a point z0, if f of z satisfies CR equations at a point z0, if f of z satisfies CR equations at a point z0, then f of z may or may not be differentiable at z0. Then f of z may or may not be differentiable at z0. Next note, if f of z satisfies CR equations at z0, if f of z satisfies CR equations at z0, if f of z satisfies CR equations at z0 and ux comma uy comma, you need not write u and v. Instead of that, you can write this. If f of z satisfies CR equations at z0 and ux comma uy comma vx comma vy are continuous at z0, ux comma uy comma vx comma vy are continuous at z0, then f of z is differentiable at z0. Then f of z is differentiable at z0. F of z is differentiable at z0. This is very powerful point. Even this is also. Point 1 is very powerful. That is CR equation statement. Point 3 is powerful. Even point 4 is powerful. So if you want to say that whether a function is differentiable or not, use CR equations. Then you can get the answers very easily instead of going for limit definition. If you feel that limit definition is so flexible, do it. Otherwise, you follow CR equations in the analysis of whether a function is differentiable at a point z0 or not. Next note. If f of z does not satisfy any one of CR equations at z0, if f of z does not satisfy any one of CR equations at z0, then f of z is not differentiable at z0. If f of z does not satisfy any one of CR equations at z0, then f of z is not differentiable at z0. Then f of z is not differentiable at z0. Now let us take an example. Earlier we have seen the example of f of z equal to z bar. So when you try to get its derivative using limit definition, we got limit h tends to 0 h bar by h. Then people got confused in this case. Now let us overcome this confusion by applying CR equations, right? Now here, what is z complex number? X plus iy. Apply conjugate. This becomes x minus iy. Therefore, this f of z equal to x plus I into minus y. Now this is u of x comma y, and this is v of x comma y. Therefore, here u equal to x, v equal to minus y. Now here ux equal to 1 and vy equal to minus 1. So here dou u by dou x is 1, dou v by dou y is minus 1. Therefore, the first CR equation is failed. Ux is not equal to vy for all points x comma y belong to R square. So therefore, ux is not equal to vy. So this is a constant expression. This is a constant expression. So these two quantities will never be equal. So for all points x comma y belong to R square. That means first CR equation itself getting failed. Therefore, f of z equal to z bar is nowhere differentiable. Is nowhere differentiable. Nowhere differentiable means it is not differentiable at all points. It is not differentiable at all points. So therefore, this is the magic with CR equations. If x is not equal to vy, so because at all points, therefore it is nowhere differentiable. Nowhere differentiable means it is not differentiable at all points. I can't get even a single point where the function is differentiable. Z bar, such a worst function in the complex variables. Okay, so work out this. Bilinear transformation. Let us look at this. Linear transformation. Basically, transformation means it is a function. Since we are working with complex variables, we can express the function in the complex variable z. Linear means the degree of each variable is either 0 or 1. So the degree is either 0 or 1. In that case, this by means basically 2. That means we are working on two linear functions in the complex variable z. Suppose when you look at this, for example, 2z plus 3. Now this is a linear function in the variable z. Suppose I have another function like this. For example, 5z plus 9. This is a linear function in the variable z. Now let us take the ratio. Suppose I call it as t of z. So this I can write it as 2z plus 3 divided by 5z plus 9. So this is a numerator is a linear function in the variable z. This is 5z plus 9. It is a linear function in the variable z. Linear means the power of each variable is either 0 or 1. Here the power of z is 1. Here the power of z is 1. So both are linear functions. So this is one linear function. This is another linear function. That means we are working with two linear functions in the variable z. When you look at the condition 2 into 9 minus 3 into 5, this is not 0. Therefore, this is an example of a bilinear transformation. Hope you understand this. Now I go for generalization. A function of the form or a transformation of the form t of z equal to az plus b by cz plus d. Az plus b by cz plus d is called a bilinear transformation if a into d minus bc is not equal to 0. So therefore, a into d minus b into c should not be 0. In that case, this is called a bilinear transformation. Bi means 2. Linear transformations means degree can be either 0 or 1. So this is one linear transformation because the degree is 1. This is second linear transformation, degree is 1. When you find the ratio 2z plus 3 divided by 5z plus 9. Now here 2 into 9 minus 3 into 5 is non-zero number. 18 minus 15, it is non-zero. Therefore, this is an example of a bilinear transformation. So if I define in general, it will be like this. A transformation of the form t of z equal to az plus b by cz plus d, where ad minus bc not equal to 0 is called a bilinear transformation. Okay, write this definition. A transformation of the form t of z equal to az plus b by cz plus d. A transformation of the form t of z equal to az plus b divided by cz plus d is called a bilinear transformation. A transformation of the form t of z equal to az plus b divided by cz plus d is called a bilinear transformation where ad minus bc not equal to 0. Where ad minus bc not equal to 0. Write this example. T of z equal to 2z plus 3 divided by 5z plus 9. 2z plus 3 divided by 5z plus 9. 2 into 9 minus 3 into 5 not equal to 0. So it's a bilinear transformation. Now let us make some comments on bilinear transformations. Suppose T1 of z comma T2 of z are two bilinear transformations. This is bilinear, this is bilinear. Then when you look at T1 of z plus T2 of z, this may not be a bilinear transformation. Similarly, T1 of z minus T2 of z, this may not be bilinear. Now replace this by dot. T1 of z into T2 of z. This is again not a bilinear transformation, but when you apply this function T1 circle T2 of z, this is nothing but composite of mappings. So this is one bilinear, this is another bilinear. So one of the famous operation we use frequently between functions is composite. So T1 circle T2 of z, this is nothing but T1 of T2 of z. So therefore, when you apply composition between two bilinear transformations, this is always bilinear. That is, a composite of two bilinear transformations is always bilinear. But when you add two bilinear, the result is not bilinear. Subtraction, multiplication, when you multiply two bilinear transformations, the degree of z will be 2. When the power of z is 2, it cannot be bilinear. The same case with minus. When you are subtracting one bilinear from one bilinear transformation, the denominator expressions will be z square terms. Here also in the denominator you have z square terms. Therefore, normally sum of bilinear is not bilinear. Difference of two bilinear is not bilinear. Product of two bilinear is not bilinear. But when you apply composite between two bilinear, the result is always bilinear. This is most effective point. Okay, note these points. Note, if T1 comma T2 are two bilinear transformations, if T1 comma T2 are two bilinear transformations, then T1 of z plus T2 of z, point 1, then T1 of z plus T2 of z is not bilinear. T1 of z plus T2 of z is not bilinear. Second point, T1 of z minus T2 of z is not bilinear. T1 of z minus T2 of z is not bilinear. Point 3, T1 of z dot T2 of z is not bilinear. Point number 4, T1 circle T2 of z equal to T1 of T2 of z is a bilinear transformation. T1 circle T2 of z equal to T1 of T2 of z is a bilinear transformation. That is, composite of two bilinear transformations, that is composite of two bilinear transformations is again a bilinear transformation. Composite of two bilinear transformations is again a bilinear transformation. Okay. Now let us start the classroom workbook based on the basics what we have seen in the last 3 sessions. Okay. Just go through classroom workbook. Question number 1. I power I, where I equal to square root of minus 1 is given by I power I, where I equal to square root of minus 1. Actually, this is nothing but power of a complex value. When you try to find powers of complex numbers, use the concept e power I theta equal to cos theta plus I sin theta. E power I theta equal to cos theta plus I sin theta. Now when you go through options, option A 0, e power minus pi by 2, 1. This is very frequently question they were asking for all branches. Every year they were giving this question for any one of the branch, right? Let us handle this. So here we were trying to find powers of a complex value. So let us apply e power I theta equal to cos theta plus I sin theta. Now in this expression, when theta is pi by 2, 90 degrees, then this becomes e power I pi by 2 equal to cos pi by 2 plus I sin pi by 2. Cos 90 is 0, sin 90 is 1. Therefore, e power I pi by 2 equal to I. Therefore, I power I is, in place of this base value, I can write e power I pi by 2. This base I is replaced by e power I pi by 2 because of this whole power I. So this is e power I into I square. I square is minus 1. So therefore e power minus pi by 2. So when you are trying to find powers of complex variables, use the result e power I theta equal to cos theta plus I sin theta. Then replace theta by pi by 2 because I want expression for I. When theta is pi by 2, cos 90 becomes 0. Sin 90 is 1. Therefore, the value of I is e power I pi by 2. Therefore, in place of this base I value, I can write e power I pi by 2. E power I pi by 2 whole power I. I into I square. I square is minus 1. Therefore, this is e power minus pi by 2. Therefore, option B is right answer. Note this. Through question number 2. The modulus of the complex number the modulus of the complex number 3 plus 4i divided by 1 minus 2i. We need to find the modulus of this complex number. One way is, this is not directly in the form a plus bi. One way is to go for rationalization. When you rationalize this, you will get complex number and then apply modulus. Another one is, this is in the form z1 divided by z2. So z1 is numerator, z2 is 1 minus 2i. So they were asking modulus of z1 by z2. So modulus follow linear property with respect to division. So this is mod z1 divided by mod z2. Now modulus of z1, this is square root of 3 square plus 4 square divided by modulus of this. This is square root of 1 square plus minus 2 whole square. So this is 5 divided by square root of 5. Therefore this is square root of 5. So therefore option B is right answer. Just we have applied linear property for modulus. And then you will get this. Modulus of z1 by z2 is mod z1 by mod z2. This is z1, this is z2. Apply square root of a square plus b square definition. We are getting square root of 5. Note this. Z equal to 3 times I power 30 minus I power 19 divided by 2i minus 1. So it is simplified to Z is 3 into I power 30 minus I power 19 divided by 2i minus 1. Now use the concept I square equal to minus 1. So here this Z is, this I power 30 we can write it as I square whole power 15 minus this we can write it as I power square whole power 19 I power 18 but into I divided by 2i minus 1. Therefore Z equal to I square is minus 1. Minus 1 whole power 15 minus 1. So minus 3. This is minus 1 whole power 9. Minus 1 minus into minus plus. So minus 3 plus I divided by 2i minus 1. But answers are given as a simple complex number a plus ib. Now rationalize this. So here Z equal to I minus 3 divided by 2i minus 1. The denominator rationalizing factor is 2i plus 1. So multiply with 2i plus 1, divide with same expression 2i plus 1. I into I, 2i square. So this is 2i square plus I minus 6i plus 3. So this is minus 3 divided by this is 4 into I square minus 1. So I square is minus 1. Minus 2 minus 3 minus 5. This is minus 5. This is minus 5i. Here I square is minus 1. So minus 5. Therefore this is 1 plus I. So therefore the value of Z is 1 plus I. Therefore option D is right answer. Just we have used I square is minus 1 and then go for rationalization. You will get Z value as 1 plus I.